Today we will see what is meant by the singular point. So before that we should know what is phase plane, phase trajectories and phase portrait. So that part we will see first. The phase plane method of analysis is the graphical method for analysis of linear and non-linear systems. So the analysis is carried out by constructing phase trajectories. So it gives the idea about the transient behavior and the stability of the system. The dynamics of control system can be represented by the differential equations. So a second order linear system can be represented by the differential equation as d2x by dt square plus 2 zeta omega n dx by dt plus omega n square x is equal to 0, where x is one of the system variable, for example displacement in mechanical system or current etc. Zeta is the damping factor or ratio and omega n is the natural frequency of oscillations. The state of above system, that is represented by equation 1, can be described by choosing two state variables. In state space modeling using phase variables, we choose one of the system variable and another one is its derivative, that is second state variable. Let x1 and x2 be the state variables of the second order system. So here x1 is equal to x and x2 is equal to dx by dt. So putting this in equation 1, we get another equation as x2 dot plus 2 zeta omega n x2 plus omega n square x1 is equal to 0. The state equations of the system can be obtained from equations 2 and 3, and these are x1 dot is equal to x2 and x2 dot is equal to minus omega n square x1 minus 2 zeta omega n x2. So for linear systems, the state equations are a set of first order linear differential equations, and solutions of state equations can be easily obtained by integration. But for the nonlinear systems, the state equations are a set of first order nonlinear differential equations, and solving these will be difficult task. Hence, for nonlinear systems, the phase plane method of analysis will be useful tool. The coordinate plane with the state variables x1 and x2 as two axes is called as phase plane. That is, in phase plane, x1 is represented along x-axis and x2 along y-axis. So it can be as shown. So here we can see that x1 along x-axis and x2 along y-axis. So that is called as phase plane. The curve describing the state point x1, x2 in the phase plane with time as a running parameter is called phase trajectory. That is, locus of state points x1, x2 in phase plane is called phase trajectory. A trajectory can be constructed in phase plane for each set of initial conditions. Hence, a family of trajectories can be constructed for a system in phase plane, and such a family of trajectories is called as phase portrait. So, starting the bit singular points, you should be aware of what is the phase plane analysis, what are the phase variables, and what is meant by phase portrait. So all these things should be known. Now let us see what is meant by a singular point. So a point in the phase plane at which the derivative of all state variables are 0. So that is called as the singular point. It is also called as equilibrium point. So since the derivative of all the phase variables are 0, so system state variables remains unchanged. The singular points are classified as nodal point, saddle point, focus point and center or vortex point depending on the eigenvalues of the system matrix A. So we know that what is meant by the eigenvalues. So if we see the characteristic equation, that is the differential equation that is representing the dynamics of the system. So the factors of that characteristic equations are nothing but the poles. So these are also called as the eigenvalues. So remember that a second order system has two eigenvalues and phase plane analysis is represented only for second order system. Now let us see what is the phase portrait for the different types of the eigenvalues of the system. So here we can consider the table, that is 3 columns: eigenvalues of the system matrix, then type of singular point and the phase portrait of system with singular point at origin. So here we can see that first condition, that is the eigenvalues of the system matrix are distinct, real and the two eigenvalues are both are negative. So the S-plane representation of the two eigenvalues can be as shown in the figure. Now this type of singular point is called as stable node and the phase portrait of the system that can be represented as shown in the figure. So this is the first type, that is depending on the nature of eigenvalues of the system matrix, how the singular points or phase portrait will seen and what is the particular name of that particular singular point. So that part we are discussing. Now another type is that is the eigenvalues of the system matrix are distinct, real and both are positive. That means the S-plane representation of the eigenvalues are as shown in figure, that is they are lying in the RHS of the S-plane. So that singular point is called as unstable node and its portrait is as shown in the figure. Now third type, that is distinct, eigenvalues are distinct, real, one eigenvalue is positive and another is negative. So such type of equilibrium point is called as saddle point and its phase portrait will be as shown in the figure. Next one is the eigenvalues are complex conjugate with negative real part. That means the poles are lying at the LHS of the S-plane. So that type of singular point is called as stable focus and the stable focus can be represented by its phase portrait, that is in standard form as shown in the figure. Now next one is the eigenvalues are complex conjugate with positive real part. So for this the eigenvalues, the singular point that is called as unstable focus and its phase portrait can be as shown in the figure. So remember what is the difference between stable focus and unstable focus. So if we see the phase portrait of the stable focus, the phase portrait is converging towards the origin and here for unstable focus the phase portrait is diverging, that is it is moving away from the origin. So that is the difference. Then if the eigenvalues are purely imaginary and conjugate, so that means the pole S-plane representation of poles is as shown in the figure. So they are lying on the imaginary axis. So such type of singular point is called as center or vortex point and its phase portrait can be as shown in the figure. So that is the singular point, and its what is the difference in the phase portrait. So depending on this, we have to solve the numericals, that is based on singular point. So let us see one example. So determine the kind of singularity for each of the differential equations. First equation is given as y double dot plus 3y dot plus 2y is equal to 0. Now see, for finding the singularity for the given differential equation, first we have to check what is the order of the system. So obviously here it is the second order system, so it will have the two state variables. So let x1 is equal to y, that is first state variable. So x1 and x2 be the two state variables. So let us say x1 is equal to y, that is first state variable, and x2 means the derivative of the first state variable. So x2 equal to y dot, that is equal to x1 dot, and obviously y double dot will be x2 dot. Now to find the kind of singularity, find out the eigen values. So here from the given equation, y double dot means d2y by dt square and y dot means dy by dt. So the given equation is, or it can be represented as s square plus 3s plus 2, that is equal to 0 in s domain. So it has the factors s plus 2, s plus 1, that is equal to 0. So from this we can have s equal to minus 2 or s equal to minus 1. That means the eigen values for the given system are lambda 1 is equal to minus 1 and lambda 2 is equal to minus 2. So if we draw the if we place the poles in the s plane, so they will be represented as in figure. So that means both the poles are negative, eigenvalues are negative, they can be represented on the LHS of the s plane. So if we see the standard phase portrait, so it will be like this, is nothing but it is representing the stable node. So remember that first we have to locate the eigenvalues in the s plane. Depending on that, find out the singularity point, and according to that we have to draw the phase portrait. So that is the procedure by which we can find out the singularity. Now again we will consider second example. So find out the singular points for the following system. So the system is represented by x double dot plus 0.5 x dot plus 2x is equal to 0. So again we can see that here it is the second order system. So state variables are x1 equal to x and x2 equal to x dot. So given differential equation can be represented as d2x by dt square plus 0.5 dx by dt plus 2x is equal to 0. So by taking Laplace transform, so we will have the equation, that is differential equation in terms of s square plus 0.5s plus 2 equal to 0. So find out the roots. So two roots will be there. So minus b plus or minus under root of b square minus 4ac divided by 2a. So by solving this we will get the two poles or two eigenvalues, minus 0.25 plus minus 3919. Now we have to plot these poles in the s plane. So that can be represented pole. Here we can see that poles are lying in the LHS of the s plane. So according to that, this is nothing but that singular point is called as stable focus, and its phase portrait can be represented as shown in the figure. So thus we can solve the numericals or find out the singular points.